Welcome to Quantum Field Theory, Lecture 21. In this lecture, I will be talking about the so-called Renormalization Group. As a review, consider that we discussed in the lecture before that in quantum field theory, we usually encounter divergences which require renormalization. Renormalized expressions generically involve an arbitrary scale mu bar, and physical observables cannot, by definition, depend on an arbitrary scale. However, parameters that we write down in the Lagrangian of the field theory can depend on this arbitrary scale. As an example, we found in lecture 17 that the independence of the physical quasi-particle mass with respect to the arbitrary scale mu leads to a condition on the parameter in the Lagrangian, which we call m physical, that was given by the equation that's written in equation 21.1. In the last lecture, lecture 20, I think, yes, lecture 20, we found that the independence of the physical vertex led us to a condition on the physical coupling that appears in the Lagrangian that's given by equation 21.2. These two examples represent the dependence of the Lagrangian parameters on an arbitrary scale mu bar. The consequence of these equations is that the parameters lambda physical and physical change with mu, and we call lambda physical and m physical the running coupling constant and the running mass. It is also customary to introduce new symbols called the beta and gamma functions of the theory that are basically the derivatives of these coupling constants and masses, where we sort of multiply the derivatives with respect to the same parameter such that this derivative doesn't change the mass dimension of the parameters. So let us now consider a physically measurable object, for instance, such as the pressure in quantum field theory. When we calculate the pressure in quantum field theory, as we have done in previous lectures, we typically encounter divergences that require renormalization. After the renormalization, the pressure will depend on parameters in the Lagrangian, such as lambda physical or m physical, as well as an explicit dependence on the renormalization scale mu bar. Nevertheless, the pressures are physical observable, so choosing a different scale, so replacing mu bar by mu bar prime, must give the same pressure. So we can write that the pressure, which is a function of mu bar and the parameters lambda and m evaluated at mu bar, must be the same as the pressure evaluated at a different scale mu bar prime and the parameters evaluated at a different scale mu bar prime. So put differently, a physical observable is invariant under the changes of the renormalization scale. Because of this invariance, we call this invariant under the renormalization group. For the case of the pressure, the renormalization group invariance implies that the total derivative d by d mu bar of the physical observable has to be 0. We can use the chain rule to split up the total derivative in its part, so we can split d by d mu absolute in terms of the partial derivative d by d mu bar that acts only on the explicit dependencies of mu bar and the pressure, and then a derivative with respect to lambda physical times the beta function, and a derivative with respect to the mass times the gamma function. Of course, this rule generalizes to systems that have multiple coupling constants and multiple masses, for instance. So for the case at hand, it is slightly easier to discuss the entropy density, which is the temperature derivative of the pressure. The reason for doing this has to do with the issues surrounding the cosmological constant. But if we do this, and we use the expression that we found for the perturbative pressure to first order, which is given here, we have that the first order perturbative entropy density is just given as this expression listed in equation 21.8. So recall that this function JB here is a function that just depends on explicitly T and M. It doesn't depend on mu bar. So if we want to calculate the derivative of this physical observable, the entropy density with respect to mu bar, this first term drops out completely. And all the mu bar dependence in that second piece here, where IB again is a function that does not depend on mu bar, must come from the dependence of mu inside the expression of the free propagator. So we find that the derivative of the entropy density with respect to mu bar is given by the equation 21.9, where the derivative acts on G free. We can then use the explicit form of the free propagator evaluated at 0 that we found in lecture 15, specifically equation 15.16, and we find that the corresponding result is just this m squared over 8 pi squared here. So then the invariance of a physical observable, such as the entropy density here, implies that the left-hand side here must be equal to the derivative with respect to the coupling and the derivative of with respect to the mass of that same observable multiplied by the respective gamma and beta functions of scalar field theory. So this is a condition for the theory to be RG invariant. We can now check whether this condition is actually fulfilled using the result that we already have. To that end, note that the lowest order perturbation theory, the coupling in the Lagrangian lambda and the physical coupling are the same, and so are the masses. Corrections only come in at higher order in the coupling. Also recall that if we look at the explicit expression for the beta function that is given, for instance, in equation 21.2, the beta function is order lambda physical squared. So the term that appears here is order lambda squared, whereas the left-hand side here is only order lambda. So this is a higher order term that we can neglect to leading order in perturbation theory. Also, the result for the gamma function by similar argument is order lambda physical, so first order in perturbation theory. So that means that consistently we find the following equation has to be true in order for our result for the entropy density to be RG invariant. We can evaluate this derivative over here, and we find that the derivative over here will just bring down the derivative of this derivative of the function JB with respect to T. Since these two, the mass and the temperature, commute with each other, we can exchange the derivatives, and we find that this is the same as d by dt of the derivative of JB with respect to mass, but that function is just nothing else but 1/2 the function IB that we defined earlier. So long story short, we find that the right-hand side here is given by 3 lambda physical over 2 pi squared and physical squared over 2 times the derivative of IB with respect to T. And you should compare this to the left-hand side here, which is exactly the same expression. So we find that indeed the result that we found before for the first order perturbative pressure in scalar phi 4 theory indeed is RG invariant to lowest order in perturbation theory. So what does the Renormalization Group do for us? Well, first of all, it provides a check, a consistency check on results that we have obtained, for instance, in perturbation theory. We can use precisely the same logic that we now used for the entropy density for other quantities, and we can check whether those quantities fulfill RG consistency, that the derivatives with respect to the explicit dependence on mu cancels again against the corresponding dependencies that we get from the beta and gamma functions of the theory. Maybe more importantly, the RG equations imply evolution equations for the parameters in the Lagrangian, lambda physical and m physical, that we started out with at the first slide in the lecture today. Let us now look at one of these, namely the beta function, and let us talk about the consequence for the so-called running of the renormalized coupling in vital to 4 theory. So if we take the equation 21.2 and we ignore higher order perturbative corrections that we can do if we have a theory that's at very weak coupling, we may rewrite this equation in terms of the following result. We just put the lambda physical on the other side, and we can write this derivative with respect to logarithm of mu bar as minus the derivative of the inverse coupling with respect to logarithm of mu bar. Now, we can just solve this differential equation by directly integrating with respect to logarithm of mu bar. And we find that the lowest order perturbation theory, lambda physical as a function of mu bar, is given by this expression here, where because it's the first order differential equation, we have one integration constant, and we call this integration constant mu0 under the logarithm. Note that we've chosen the integration constant such that it appears under the logarithm, and as such, the dimension, mass dimension of that constant is the same as mu bar. It's order 1 in mass dimension. We can plot this function, lambda, as a function of mu. So this is a plot that shows that as a function of mu over mu bar. So we find that for small mu over mu bar, small energy scale, decoupling is small. So in this regime here, and then it gets larger as mu gets closer and closer to mu bar and becomes very large at mu bar. Sorry, at mu0. The upshot of this is that the renormalized coupling constant lambda physical is small at small energies mu bar. Decoupling grows as a function of the energy scale mu bar. That's just saying again that the coupling is running. And we can easily associate this increase of lambda as a function of mu with the positive sign of the beta function. By contrast, if the beta function would have a negative sign, this just flips the direction of the running of the coupling, and the coupling would be decreasing as a function of mu bar. Note that positive beta function implies that the physical coupling of the theory just gets stronger at short distances because higher energy correspond to smaller distances. This is a problem if we want to think about the continuum limit of the peak theory, because as the energy scale at which we consider processes in the quantum peak theory gets higher and higher, this means we're probing smaller and smaller physical distance scales. And if the coupling gets stronger and stronger in that regime, we have a problem approaching very small distances using our perturbation around zero coupling. So that's part of the problem. The opposite case, where the beta function is negative, behaves much nicer in this regard. The coupling decreases at short distances, which means that as we approach the continuum limit, the small distance limit of the theory, the corresponding coupling will be extremely small. So the theory is weakly coupled in the continuum limit. So this is basically where our methods of perturbation theory work best. Another term for theories that have a negative beta function are those that we call these theories asymptotically free, which is just saying that the coupling gets smaller as we approach small distances. Let us return to the case at hand where we analyze the beta function of phi-4 theory to leading order perturbation theory. I said that the coupling gets very large as we approach the scale mu0, our integration scale mu0. In fact, that if we sit at exactly the point mu bar is mu zero in the expression that we had for lambda physical, the coupling actually diverges. We call the corresponding point where the coupling diverges the so-called lambda pole, because the coupling has a pole there, and lambda was the first one to really describe the physics behind this. Since the beta function was calculated in perturbation theory, we can't really trust our results to correctly identify that behavior close to the lambda pole. Okay, so the lambda pole is a regime where the coupling is extremely large. Our analysis was done assuming that the coupling was very, very small. So clearly, our method is not good at discussing the physics of the lambda pole. So we don't really know whether the theory actually has a lambda pole or whether this is just an artifact of our perturbative expansion. However, if there really is a lambda pole, then what that means is that there is a scale, a minimum length scale, below which the coupling doesn't really make any sense. Okay, so if we go with mu above this point, above the lambda pole, then really the coupling sort of changes from plus infinity to minus infinity, or does something extremely weird. The theory really is not defined for length scales smaller than this. So basically what that means is that below a certain length scale, so think of a lattice, below a certain length scale, the theory doesn't exist. And we can only treat the theory on a lattice with this minimum length scale or larger. So in this sense, we are talking about an effective theory, a theory where you cannot take the continuum limit. While for phi-4 theory, people argue in favor or in disfavor of the existence of a lambda pole, there are very strong arguments suggesting that another theory that we actually like a lot, namely QED, has a lambda pole, and that theory really is not properly defined in the continuum limit. Now that need not necessarily be a problem. So if we, for instance, think of QED to be part of a bigger quantum field theory that has additional parts that then will regulate the beta function somewhere, then this still lets us use QED as an effective theory at low energy or large distances. But it just says that QED on its own, without anything else, doesn't really make a lot of sense. And this concludes the present